Well, thank you very much for inviting me to present today. So with all the talk about advanced reactors, and we're going to hear about those next, is there still any interest in light water reactors? Well, this is the reason why. So light water reactors, 84% of the present fleet, so there's 439 reactors operating, 84% are light water reactors. PWRs are dominant, 69%. And then if we look at new build, it's even more so. So 56 reactors under construction, 84% of those are PWRs. So PWRs are really dominant. But before we look at PWRs, what I wanted to look at was what you can do if you really try. So the left hand is the vertical axis, is the percentage of electricity from nuclear. So what happened in the 70s, there was the oil crisis, a lot of people moved to nuclear. And that's, the purple one's France. So France in the 1980s, 42 reactors were connected to the grid in the 1980s. That's one every 3 months. And they built series. So there was 28 of the 900 megawatt series, and then 14 of the 1300 megawatt series. So you can do it if you really want to. There's Germany as well there, 12 they grid connected, Japan 17, but France showed really how you can do it if you really want to. Quick reminder of pressurized water reactors. So it all starts with this. This is a fuel pellet about the size of a small fingernail. 300 of those in a tube, and you've got a fuel rod. 260 of those rods, and you've got a fuel assembly. About 200 fuel assemblies in the reactor. So about 16 million pellets, and you've got a large reactor. So PWR, most widely deployed reactor technology. We're going to hear about nuclear power submarines from Peter this afternoon. All of those are PWR powered. So it's light water moderated and cooled. So that primary circuit is pressurized and doesn't boil. And then you've got a secondary circuit which is totally non-radioactive. And note that all the balance of plant really on that secondary circuit is very much the same as a coal-fired station. So we can look at what's under construction at the moment. EPR, it started out as the European pressurized reactor, and then they renamed it to the evolutionary pressurized reactor. Then there's the advanced passive, Westinghouse, the South Korean reactor, Russia, and China. Remember, during this period, there was Fukushima and a lot of design changes for new reactors, so they had to cope with that as well as the rest of the problems. So looking at the EPR, the last reactor in France, the final N4 series, was connected in 1999. So that was 1475 megawatts. So they were designing a bigger reactor, and this was it, 1750 megawatts gross output. So it is really a very big reactor, and it's very complex. So there's basically there's two ways of achieving safety. You can either have multiple trains of safety, or you can go for more of a passive system. So EPR went for multiple trains. So it's got 4 trains. It's like the AGRs we had in the UK, everything there was in 4 trains of protection. So you've got water that can inject with pumps, etc., into the reactor if there's a problem. And note that all the pumps are outside the containment, so you can maintain them on load, but of course you now have more penetrations throughout the containment. And the containment removal system as well, the heat removal system. 2 dedicated trains with pumps and heat exchangers. There's a couple of ways in which you can cope with a core melt. You can either try and keep the melt within the reactor vessel by cooling the reactor vessel, or you can let it go out and spread it. And this one's got a corium spreading area. So it lets it go out, spreads it, and then cools it in that sort of way. So what's happened to the EPRs? So the first contract was December 2003 in Finland. And Arriva Siemens did this for a fixed price. It was 3.2 billion euros. As you probably know, it's not been a tremendous success. It's taken nearly 17 years. But last month, they did Grid Connect. I've been in conversation with them. They're really happy. They're now doing the power raising. They're 735 megawatts at the moment. It'll be in commercial operation by the end of July. I mean, they had problems with the casting. The INC problem, in November 2009, there was a joint statement by the safety regulators in UK, Finland and France that there wasn't enough independence between the control and protection systems. So there's quite a lot of redesigning there. The problem they had as well at the end was that turbine had been installed for a very long while. So when they came to do the hot tests, they found that they had to do maintenance on the turbines. So if you have a very long build, then some of the early plants, you're going to have to do maintenance on it to get it going again. But it is up and going, so that's good. Flamanville in France, you remember the last new one in France was 1999, so this was 2007. It was going to be scheduled operating in 2012, still not operating yet. Initial problems with concrete. They've had a lot of welding problems. The head's got to be replaced as well. So that one should get going next year. The Chinese ones were more successful, but still took more than the scheduled time. It was scheduled 2014, ended up in 2018. Problem at the moment with Taishan, you've probably heard that last year they had a fuel failure. Now, you'd expect with a fuel failure, you'd take it out, find the bad fuel, change it, and you go back on again. But it's still not back in operation. It's possible they've got vibration problems as well that have caused that. But the Taishan 2 is operating okay. It's generating 12 terawatt hours last year, so that one's going well. And then we come to Hinkley Point. So with all the experience of EPRs up to now, we should be able to build Hinkley Points okay. There's a wonderful program on SBS about building a nuclear power plant. If you haven't seen it, have a look at it, because it shows you just what's involved in one of these really big plants. Because the last UK plant was 1995 Sizewell B, so it's been quite a long while since after that. Interestingly, the pricing, that contract for difference, 92.5, in 2013, that was competitive with offshore wind. The wind was over 100, this was 92.5, it looked okay. Then, of course, what happened in the next few years was wind costs went really down. This started to look very expensive, and people were saying it's ridiculously expensive, we shouldn't pay so much. You look at UK today, this is really cheap. We're talking about over £200 a megawatt hour at the moment in the UK. So it's come back again, all right. The other thing about the UK is you've probably seen this announcement. We're going to have Great British Nuclear. It's going to be a new government body to be set up. Not quite the old CGB, but at least it's government funding. They've got a big program. They're putting a lot of money into it. It's going to be really interesting to see how that develops. So the next one is the Westinghouse AP1000. Design certification back in 2005. But what happened then was Post 9/11 particularly, they looked at aircraft impact on reactors, and it had to be redesigned to have a stronger containment. So in 2011, there was a new design, and that estimated about $1.5 billion to each project. It's now got a double containment. And this is a two-loop, so it's a big reactor. Completely different approach to safety. So this is all passive safety, and it's all within the containment itself. So it's got core makeup tanks, borated water. So these will all dump into the reactor vessel if there's a problem. Accumulators pressurized with the nitrogen. We've got a big water storage tank within the containment, which is a heat sink, passive heat exchangers as well. So it's got a lot of passive systems. So how do we go with the AP1000s? Well, the first deployment was in China. So that was the Sanmen plant, and that was very quickly followed by the Haiyang plants as well. And initially it went really well. So that reactor pressure vessel for the first unit was installed in September 2011 after a March 2009 start. So they were going really well. But then they had problems with the Curtiss-Wright primary cooling pumps, and they had to go back to America and be reworked. And they've had a few problems with those pumps. And that's continued a little bit as well. So the Haiyang, the Sanmen plant has had more problems with that. So the other deployment was in America. So again, this was the first deployment in America for more than 30 years. So they really were out of experience with this. 2013 started. Pretty soon they found there were supply chain problems. So Westinghouse tried to get out of that by buying up Stone & Webster, which was the nuclear construction part of Chicago Bridge and Iron. But with doing that, of course, they then took all the project risk. So it led to their bankruptcy. So this was a fixed price contract, but it's not much good having a fixed price contract if you're bankrupt. So then there was the decision about, do you continue to build or not? So Southern Nuclear took over the project, and they're continuing it. It's had the hot tests. It's should be going okay. The problem they've got at the moment is with documentation that's still not really up to date. VC Summer, they looked at the detailed schedule and cost and decided that they couldn't continue with the project, so that one was abandoned. Why did Vogtle continue and VC Summer abandon? I think there's three factors there. Vogtle's got 4 owners, so they could spread the costs more. VC had only got 2 owners. Also, Georgia Power has got 3 times as many customers as South Carolina Electric and Gas, so they could spread a rate increase. And the final one was Toshiba Guarantee was $3.7 billion for Vogtle, 2.2 for VC. So the next one's the Korean AP 1400. So going back to 77, Westinghouse, PWR built in South Korea. They tried Candu, tried French PWRs, developed themselves, so that OPR 1000 they developed, 12 of those are operating. So this gave them self-reliance and their own IP on these systems. So then they started developing this new APR 1400. So started back in 92, by 2001 it was developed, got design certification in 2002, and then the first construction in 2008. This had really got enhanced safety and larger operating margins. They really went for operating reliability in this place. Again, it's a 2-loop plant, so it's big loops, 4 primary injection trains. Interestingly, they've got 3 55% main boiler feed pumps. So to ensure that they don't have any problems with the feed system, they've got 3 pumps. So if they lose a pump, they can still continue. And they've got 4 trains of that auxiliary feed water system as well. So it's really designed for reliable operation. So the first construction, 2008, Shinkori 3, again started well, but in 2012-13 time, South Korea started running some problems with QA. They had to replace all the safety cabling, there was some faulty valves, etc. And then in 2017, they had a new president, Moon, and he wants to phase out nuclear. So it was looking pretty bad. Some of the construction was suspended. But now, this year, they've got a new president, President Yoon, and he's pro-nuclear, and he's now continuing all the domestic construction, and he wants to really push for exports. And it's a really good time because Russian reactors are now a lot less attractive, so it's a good time for them to get into this sort of market. And they were one of the few contractors that had export success. So the UAE decided in 2008 they would go nuclear, and they did it really quickly. So 2008 the policy, 2009 they put the regulator in place. What they basically did was buy the best worldwide. So they got a regulator from the NRC, they got John Loy from Panzer. They just bought the best they could to get it really, really quickly done. And 2009, they placed a contract with KEPCO. So it's a $20 billion contract for 4 reactors. And as soon as they got the construction license in 2012, the day after the concrete was poured, and construction went pretty well. So by March 2018, it was completed. But then you see that they didn't get an operating license until February 2020. And operational readiness, stopped them going to power. So this is a big point of a reactor. It's not only constructing the reactor, it's the operational readiness, training the staff. They've got to be appointed early. They've got to be involved in commissioning because that's where they really get experience. And this is what we did at Opal. The operating staff were appointed during construction, went through all the commissioning, saw all that. We were ready. As soon as you got the operating license, we were away. Here's Russia. So VVER is water-moderated, water-cooled energy reactor. So it's a PWR, a Russian PWR. First one operating in 1964. They had a 440 series, which they exported to a lot of countries. And that was followed by 1,000 VVR 1000 series. And there's 31 units of those operating, including the 15 in Ukraine. All those in Ukraine are VVR 1000s. So from that, they developed this 1200. One feature of this that's different from most PWRs is the steam generators are horizontal. They think you can support it better with horizontal than vertical. So that's the reason. So the first construction, Russia in 2008, operating in 2016. What usually happens in Russia is they run out of finance. So finance is always a problem. But what they do is export. So they've been very successful with their exports. So there's reactors under construction in Belarus, Bangladesh, Turkey. And I expect Helen will tell us about Egypt this afternoon as well. And the reason, of course, it's so attractive is the loan you get. So it's a state loan from Russia. It's at a low rate. It's a very long time. So this is what makes it really, really attractive for Russian reactors. And so to China. So China was relatively late into nuclear power. Daya Bay, PWR in 1987, and they bought reactors from all sorts of vendors. You know, they tried Candu, they tried Russian, AP1000, DPR, plus their own designs. In 2001, they had 3 reactors operating. They've now got 53. So you can see the sort of program they've had in China. What happened with these reactors is CGN were developing from the CPR 1000 to the latest 1000. CNNC were also developing their reactor. And the NEA said, look, it's silly. We've got all these multiple 1,000 megawatt designs, rationalize them, and then we'll be able to export them. So that's what they did. So it's PWRs based on French reactors, basically. So the first one started construction in 2015, grid connected in 2020. So this is a first of a kind reactor grid in 66 months, which is pretty good going. And then they've got a big series now under construction. And also, you know, at the same time as they were building in China, they were building in Pakistan. So it's very much the same year they started. 67 months for a first of a kind in another country. So that they are pretty well organized at building reactors. Interesting to see that that Karachi 3 grid 4th of March 2022, full power 31st of March. That's a very short time. Most reactors would do a lot of power raising tests and have intervals where the regulator says you've got to pass various things before they get. That was a month to commercial operation, so that's probably a bit quick. And more. So there's a contract signed with Argentina in February of this year for the Tusha site. So that's likely to be the next one. So what I've done is compared the large reactor parameters. So you can see that basically all the reactor conditions, primary coolant conditions, are about the same. So the efficiency of these reactors are about the same. But you can see how much bigger the EPR is than any others. Safety, still mainly by multiple trains, but some incorporating in passive as well. And you can see from the shortest time to grid that a conservative design and building a series certainly works the best. So what's happened to PWRs? Well, some of the reactors have restarted in Japan, but they're all PWRs that's restarted. But what people forget is that there are actually 2 ABWRs under construction in Japan. These are GE Hitachi ones. Construction suspended, of course, post-Fukushima, but now being completed, and they've applied to restart these, or to start them up first time. So that's going to be interesting. What we've seen is that there's really 3 challenges with large reactors. There's the high cost. You've probably heard Hinkley Point C is equivalent of 42 billion Australian dollars. I mean, it produces 26 terawatt hours a year, so it's a really big reactor. But there's a lot of cost. High construction time, so we've seen the best is 5 years. The worst can be a lot more than that. And they can be too big for small grids like Australia. So there's been this increasing interest in small modular reactors. Less than 300 megawatts typically, but as we'll see, some are a little bit more than that. Because they're small, it's very easy to get a high level of passive safety. You factory build them, transport them to site, so you've got reduced on-site construction time and more certainty about your construction time on site. And we're looking really at multi-purpose now, load following capabilities, as Stephen said. So as Stephen said, the leading example is NuScale. So this module fits in this big pool of water. Those of you know Opal, this is 70 Opal pools in that pool. So there's a lot of water there. 12 module plants supplying about a million homes. So this was the first SMR to achieve US NRC design approval. And they did it pretty quickly. The GDA was accepted in March 2017, and September 2020 they issued the GDA. So that's 3.5 years for a new design reactor. So the NRC did pretty well actually in that. And this is the first deployment. This is for UAMPS, consortium of 45 Western community-owned utilities providing wholesale electricity to eight states. 6-module plant. What they've just done, February 2022, is done the site field work completed. So they're preparing the site. Should put in a COLA in 2024, first module operating in 2029. GE Hitachi, been designing PWRs since the 1950s. So unlike some of these SMR vendors who are really startups, this is a really experienced reactor designer. They know all about supply chains. They know how to design to cost. And this was really designed to cost. So it's been selected by Ontario Power Generation for the Darlington site. So that site already has got an environmental assessment, and it's got a site preparation license. So that's a big advantage in getting started. March 2022, contract placed for site preparation. So that one really looks as if it's going ahead, operating by 2028. So Canada has got, you've probably seen last month they published their strategic plan with 3 streams. Canada's very well organised with SMRs, and they're really, really pushing it. There's also agreements to deploy this PWR X300 in Poland, and probably TVA as well in the US. Here's a really experienced nuclear designer. So they really, Rolls-Royce, synonymously with engineering, builds all the UK nuclear power submarine reactors. And the UK government are really supporting this. So 470 megawatts, it's a big SMR. What Rolls-Royce have said is that what they wanted to do was to still make it transportable by road, but to try and optimize the turbine as well. So it came out as 470. And that's just gone into the regulator GDA process in the UK. So it's just been accepted by ONR, the Office of Nuclear Regulation in the UK, literally just this last week. As previously mentioned, the Australia-UK Partnership Agreement includes SMRs as well. Here's one under construction. So this is in China. Looks very similar to the B&W mPower, the ones that ran out of finance in the US. Actually been under development since 2010. Designed very much as multi-purpose, so steam heating, because that's really important in China, and desalination. Integral reactor again. So that's very much a demonstration plant. And here's another one under construction. This is one of the earliest concepts. This dates back to 1984. And this is our friends at CNA INVAP who built Opal. The problem in Argentina is they repeatedly run out of money. So this project start. It's just restarting again. I mean, construction started in 2014, and as you can see from the photo, it's not quite finished yet, so it's going to be a little bit of time. And here's the one in operation. So Russia uses these KLT-4DS reactors for their icebreakers, so they thought, wouldn't it be a good idea to put a couple of these on a non-powered barge, and then we've got floating nuclear power. And this has been working since 2019. And Pevek is the most northern city in Russia. So this is an area actually where heating is not just a luxury, this is a necessity. You know, typically it's about -25, so it's, you know, they really appreciate the heating. So a few conclusions. If you don't keep doing it, you lose experience, you lose the staff, and it's then very difficult to get back going again. The good thing is that once you've got your first of a kind going, you've got the experience back, and you should do better. So a lot of these programs now have got through the first of a kind, and we're emerging into a better area. Certainly post-Fukushima designs, changes, extended some build programs, because all the regulators and operators and vendors looked at their designs and said, you know, what do we have to do to make sure that in the very worst accident situation it's okay. Conservative design and series build is definitely the best, and try and keep it simple. You know, we build, engineers like complicated things. You've got to really keep it simple. PWR is still the dominant design, and as we've seen, operational readiness is just as important as construction efficiency, because when you've built it, you want to immediately start it up. And we've seen now that the first commercial SMRs are very close to deployment. In the next few years, we're going to see quite a few SMRs operating. And I think that's going to be one of the really good futures of nuclear. Thank you.